Okay, welcome to Time Value of Money, Chapter 9, Introduction to Business Finance. All right, so far we've been focused primarily on the past and the present, and we want to start looking towards the future. So let's jump right into that. So what's the value of $100 in a bank account with a 6% annual interest rate after 1 year and then after 2 years? Well, I think we can all agree that after 1 year, it's pretty clearly $106, which we can get to by taking 100 plus 6% of 100, and maybe a nicer way to put that together is in this little piece of equation, and we get our $106. And after 2 years, it actually depends on what our contractual framework is. It depends on what our definition of annual interest rate is. And there are two common types of interest: simple interest and compound interest. And in a simple interest world, or in the real world, a simple interest contract, the contract would read something like, you put in an amount of money, say $100, and we, the borrower, will, every year you keep that $100 with us, we will give you 6% on that original $100. So after 2 years, you would have accumulated $6 plus $6, or $112. Much more common are contractual frameworks made of what we call compound interest. And in compound interest frameworks, the total amount in an account collects interest. So let's see how that works. So after 1 year, EOI stands for end of year. The end of year balance is going to be just what we saw before, $106. But now for the second year, that whole $106 is accruing interest. So we have to take the 106 that we started the beginning of the year with and multiply that by 1 plus 6%. And that's going to give us a little bit more than $112, $112.36 to be specific. Okay, so as usual, it's always good to think a little bit once we learn some new stuff, think about the implications. In this case, I'm asking which is best for lenders or for borrowers? Well, I would say if you are a lender, compound interest is going to be better for you because you're going to get more back in the future here. So if you're a lender, you want to say compound. And if you're a borrower, you want to say simple because you'll be paying less back in the future. Okay, so let's look at our future value formula for compound interest. What I mean by that is I'd like to take what we've done here for compound interest and make a general formula out of it. So when we do something like this, taking a simple example and generalizing it, we say this is a heuristic method for what it's worth. So anyway, at the end of 1 year, we're going to have 100 times 1 plus 6%. And at the end of the second year, we have that 106 times 1 plus 6%. But what is 106? Well, we know it's equal to 100 times 1 plus 6%. So we can substitute that in and simplify that a little bit. And we know now at the end of the second year that we're going to have the initial amount we put in times 1 plus the interest rate raised to the power of the number of time elapsed, the amount of time elapsed. So that's pretty cool. So let's just start assigning some algebraic variables willy-nilly to what we've got on the previous page and see what we can come up with. So let's say that present value is equal to our initial investment amount. We can call that the principal at t equals 0. And we're always going to be starting projects at t equals 0. And the future value is the amount that our cash would grow to, okay, after t years or at tf. And we can define capital T as TF minus T0, or the amount of time elapsed, and we can say our annual interest rate, we can call that R. So substituting all of these things in, we get in general now, not just for 2-year cases with 6% interest and $100 starting with, but for basically any problem like this, the future value, the amount that we're going to wind up with at time t, is going to be equal to what we start with times 1 plus the interest rate quantity raised to the amount of time elapsed. And this is called the fundamental time value equation. We're going to use it a lot for the rest of this book. Okay, we could do the same sort of thing with simple interest. You're welcome to look this over. It's pretty straightforward. I also talk about it in the prose portion of the text, so you can look that up, but I'm going to skip it for right now. One of the reasons that I'm going to skip it is because compound interest is much more common than simple interest, and going forward we are going to assume compound interest unless we have some special reason not to. And the second reason I'm going to skip over the formula generation for simple interest is if you look at this graph where we have time on the x-axis and what your initial pile of $100 would grow to over time on the y-axis, you can see that with compound interest, we're growing exponentially, and with simple interest, we're just growing linearly. So this is more interesting, and it's what's much more commonly used, so that's what we're going to focus on. But key takeaway from this graph is cash is not a constant in time. Cash is an exponential function of time. Okay, so that's a key concept that you want to get there. Okay, so what else can we say about this? Now that we've all agreed that cash in a low-risk contractual framework is an exponential function of time, let's look at this equation. And what we see from the graph and what we can also intuit from the equation is that our pile of money grows bigger the longer the length of time we keep it in a guaranteed growth project, and also it grows bigger the higher the interest rate is, the more money we're going to get. So if we have a project with a higher interest rate and we let that lapse for say 7 years, let that run for 7 years, we're going to get a lot more, wind up with a lot more money than if we have a smaller interest rate. Okay, so this is just a reminder here that in a compound interest world, cash is an exponential function of our interest rate and time. All right, so what I'd like to spend a little bit of time on right now is sort of beating to death this fundamental time value equation. And what I mean by that is let's just solve it for everything we can. Let's just go back to high school algebra and move around some terms and solve for different things. Okay, so we can solve it, of course, for present value. Okay, so in a case like that, we would look at this and say for a given future value, our present value is going to decline exponentially with t. That makes sense. And that leads to the saying a dollar today is worth more than a dollar tomorrow, or receiving a dollar today is better than receiving it tomorrow. Why? If I receive it today, I can put it in an exponential growth contract, savings account, interest-bearing checking account, treasury security, CD, something like that. And then by tomorrow, it'll be worth more. So I want to receive it today because I can put it in some guaranteed investment and it will grow to more than a dollar tomorrow. Okay, a little bit on terminology. When we are calculating future values here, okay, then R, that algebraic quantity R, is called our interest rate. Okay, and because this is finance and it's kind of like accounting and we have to have more than one name for everything, you know the drill at this point. If we are solving for present value, even though R is exactly the same algebraic quantity, okay, it's referred to throughout finance as the discount rate. It's very important for you to know that this is the same algebraic quantity in either case, okay? Also, a little bit more on terminology, the present value of an investment is sometimes called the principal that we initially put into an investment, or our initial investment amount. And our future value is sometimes called the amount that our principal will grow to at time t. All right, so that's it on basic terminology. Now it's time for a couple of examples. So first up, let's say you have $207 in a bank account paying 5% interest. What will your account balance be in 3.6 years? Well, we're just going to apply the fundamental time value formula, okay, and we're going to plug in. We know our PV is, we're starting out with $207. We know our R here is 5%, and we know the time of the project we're thinking about is 3.6 years. So we plug those three things in, and we wind up with $246.74. Okay, let's try another. So we invested long ago and far away, 5 years ago, in fact, in a 2.5% CD. 5-year CD means the contract runs for 5 years, that grew to $100 at maturity at the end of the contract. So how much did we start with? Well, that's pretty easy too, using the same formula. We just use the magic of algebra to solve for the present value, the amount we started with, and we plug in what we ended up with, our 100, and now we want to divide by 1 plus 2.5% interest raised to the fifth, the 5-year term, and we come up with 88.39. Okay, so far so good. All right, and now we need to think about PV and FV in the context of finance problems a little bit. Okay, if we're using this, starting with this formula, okay, the fundamental time value formula, what this is describing is the cash in a vehicle, okay, in an investment project, let me put the word project here, in a project with a guaranteed interest rate at T0 and TF, okay? And that would be like in biology, we could look at an analogy where we take a petri dish and we put some bacteria in the petri dish, and at t=0 we count up the bacteria in the petri dish, and then at t=tf, t final, we count up the bacteria in the petri dish again. Okay, so everything's staying in the petri dish, everything's already in and staying in the bank account or the CD or whatever. Okay, so that's strictly how this formula was developed. However, in finance, many problems are concerned with not what's in the petri dish, but what we put into the petri dish and what we take out of it, what we put into our interest-bearing checking account and what we take out of it. Okay, so those are going to be the cash flows into or out of a project, and we always want to be very careful to measure the cash flows for a single person or a single entity into or out of a project. Okay, for a two cash flow project, we'll get a little terminology here, and we'll say CF0, standing for cash flow zero, is the amount paid or received by the single participant we're focused on at time t=0. Okay, and we could say CF sub TF, cash flow at time TF, is the amount paid or received by the participant at TF. Again, that's the amount taken out of or put into a project by one player at TF, and this here, CF0, is the amount paid or received by the same participant at t=0. So we're worried about flows, not the amount that's in the account. Okay. All right, so in cash flow problems, cash inflows are always assigned a plus sign, and cash outflows are always assigned a negative sign. Okay, and we'll keep that in our back pocket. Okay, but as appropriate in cash flow problems, we can replace future value equals present value times 1 plus r to the t with absolute value of the cash we take out of the project at time TF equals absolute value of cash we put into the project at t=0 times 1 plus r to the t. And because everything's so simple here, we're working with two cash flow projects, I'm just going to drop the absolute value sign here, and I'm going to say we have to use our common sense to keep track of inflows and outflows. We'll see how this works very, very quickly here. So for example, if we have a lender who's charging R% interest, okay, CF0 is going to be the cash outflow that she commits to now to receive a bigger cash inflow of CF0 times 1 plus r to the t at the future time t. Okay, so we're just going to keep track of using our common sense to know what's an inflow and what's an outflow for a particular participant or player that we're looking at. So similarly, for a borrower paying R% interest, CF0 for her is the cash inflow she gets at t=0 in return for her promise to repay a bigger cash outflow at a future time t. Okay, so if we keep our wits about us, we can work with either the FV = PV times 1 plus r to the t format, or the cash flow TF equals cash flow sub 0 times 1 plus r to the t. Either one is going to work for us. Just be careful about what's an inflow and what's an outflow if we're using the finance cash flow version of this equation. All right, so here's another example. You agree to pay 50,000 from your trust fund towards your college tuition and expenses in either 1 year or 2 years. And since your trust fund is invested in risky emerging market stocks and maybe things like Tesla that are bouncing up and down, maybe way overvalued, you further agree to set aside enough cash now so that you can guarantee you'll have the 50,000 when it's due. So in other words, you're going to take it out of all these risky investments which may crash and burn and go to zero, and you're going to set it aside somewhere now to make sure that you can pay the 50,000 in either 1 year or 2 years, okay? But you love your risky Tesla internet stock, social stock account. So you want to set aside as little as possible. So let's see what some options are. We look around and you can currently buy 1 or 2 year CDs, certificates of deposit, which yield 5.5% annual interest. That would be R equal 5.5%. Okay. And so with all that information, let's see what we can find out here. First of all, we want to identify the participant, and I want to be a little sneaky. I looked a page ahead there because we have choices for the participant. We could choose in this project, we could choose to be either you, or we could choose to be the bank offering the CD. So let's choose you. You could also we could have also chosen the CD purveyor. And either one would be fine. The key thing is we have to choose one player, one participant, and not get them confused, and stick with that one for the whole problem. Okay, is the participant a lender or borrower in relation to the CD purveyor? Well, you're going to be a lender because you're going to give them your money for 1 year or 2 years. Absolutely. So what projects is the participant considering? 1 year CD or 2 year CD. So that's you're going to do one project. You're either going to buy a 1 year CD from this bank or a 2 year CD. And should you pay 50,000 in 1 year or 2 years, and why? Okay, so remember, you want to put as little in as possible. And that clearly means 2 years. You want to give the 50,000 to your parents in 2 years. Why? Because 2 years growth means start with smaller amount. To get to 50K, because you're going to have 2 years of compound interest that you're going to enjoy instead of just one. So you can start with a smaller amount. So how much would you have to invest in the CDs in each case? Okay, so 1 year CD, you would get the PV is equal to the FV divided by 1 plus R raised to the 1. and that leads us to PV is equal to 50,000 divided by 1 plus, I don't remember our interest rate, I think it's 5.5%, yes, 5.5%, 1 plus 5.5% raised to the 1, okay, and I'll let you work out on your calculator the arithmetic for that. So for the 2-year CD, we've got the same formula, except now we have it raised to the 2 instead of the 1. Okay, so we have that nice 2 years of compound interest, and that's going to give us our PV is equal to 50 divided by 1 plus 5.5% raised to the 2. And you can see for the second one here, the denominator is bigger, the numerator is constant, so it's going to be a smaller amount that you have to put in, okay? And that's calculated for us here on the next page. Okay, so indeed, as we saw from the algebra and as we saw qualitatively, if we pay your parents, if you pay your parents in 2 years, you can set aside 45,000 now. If you pay them in 1 year, you'd have to set aside about 47,500 now. Okay. All right. So next up are cash flow diagrams. Cash flow diagrams are going to be extremely important to us throughout finance. So this is very important to understand. So a cash flow diagram is a graphical representation of a project's cash flows for one participant. And the way it works is we have time here on the x-axis, and on the y-axis we have cash flows to or from this one participant for this one project. Okay, and the way it works is negative cash flows. So cash flows away from this participant are negative, they go down, and cash flows to the participant from the project are positive and they go up. Okay. All right, this is going to be very helpful when we do discounted cash flow project evaluation methods, which are coming up shortly. And now, with all that in our back pocket, let's go back to beating this formula to death here. So now let's, through the magic of algebra, solve it for our interest rate or our discount rate. So you can check me with a little bit of algebra. We get that the interest rate or discount rate is the ratio of the future value over the present value raised to the 1 over t minus 1. Or if we want to do this in finance cash flow terms, the cash flow at the end of the project for a participant divided by cash flow at the beginning of the project for the same participant. Again, I'm ignoring that we should have absolute value signs in there, raised to the 1 over t minus 1. Okay, so let's do an example. So let's consider Velocity Advisors. They're a small-time, just-founded firm. They're guaranteeing to double your money in 20 years. And we want to know if Velocity is offering a good investment and why or why not. Okay, so think about this. Wow, double our money in 20 years. Maybe that's pretty cool. Well, actually, I really have no idea, but let's see what we can suss out here. Okay, so first off, let's go ahead and look at a cash flow diagram for this project, okay? And I've got it drawn for us already, but I want to ask the question, who is this for? Is this for velocity or is this for us? Okay, this would be for us if we participate. Okay, why is it for us and not velocity? Because we would be putting money in, we would be giving money to velocity at t equals 0, and then 20 years later we would be getting money back. Okay, all right. So that said, if we put in an amount CF0 at t equals 0, they say they're going to double our money in 20 years. So we would just simply get back 2 times CF0 at the end of 20 years. So that's our cash flow diagram for this project. Pretty simple, but very helpful. Okay, so now there are a couple ways to solve this. This is the first way I thought to solve it. Okay, so one thing that might be smart to do is solve for this project's interest rate, the interest rate we would enjoy if we did this, and compare it like we did in the first chapter, the first problem that we looked at. Compare this to the interest rate of a super safe project. And what are our super safe projects? Super safe projects are always U.S. government treasury bonds. Okay, they're not actually always the safest investment in the world, but they're always very close to it, and oftentimes they are the safest investment in the world, and so they're generally used throughout finance as a proxy for the safest investment in the world. Okay, so what we need to do is go out and look on Bloomberg or Yahoo Finance or Google Finance, the interest rate we would get on a 20-year treasury bond, and we specifically want a zero coupon bond. Why? Because a zero coupon bond is defined to just have 2 cash flows. You put money in the beginning and you get a bigger blob of money at the end. There are no intermediate interest payments along the way. So that's a zero coupon bond, and there are millions of zero coupon treasury bonds out there. So we go out and see for today a treasury bond that's going to mature in 20 years, pay us a blob of money in 20 years. We find the interest rate on that is 5%. So that's what we have it to compare to. So Velocity, since they're a new firm and they might go bankrupt, they might steal our money and take it all to Aruba or something, they better have an interest rate that's much higher than 5%. So let's find out. Okay, we're just going to solve for the interest rate, take the fundamental time value formula, solve it for interest rate, and plug in. Okay, and what do we know here? We do know that the ratio of CF TF to CF 0 is equal to 2.0. That comes from the doubling of the money. Okay, and we know that t is equal to t equals 20 years. So that's all good, and that's really all we need to get the show on the road here. So we plug in, and you should check me on this. You should always check everything that's presented in these outline notes. We get 3.5%. So we conclude very quickly that Velocity's offering is a bad idea. Okay. It's got a lower interest rate than a treasury bond, which is the safest thing around, and it's a risky startup, right? They might go bankrupt, they might be fraudulent, who knows? So that would be bad. Okay, so let's keep beating to death this fundamental time value formula. So what's the one thing we haven't solved for yet? That's t. Okay, and this is a little bit more of a hassle, and we have to use logs to make this work, but using logs and remembering, even possibly going back to our horrible memories, high school algebra books, we could solve this, and we get the time of the project. If we know everything else is the log of the ratio of future value to present value divided by log of 1 plus r. Okay, we can do that, of course, in terms of cash flows too. Okay, now we can, I gotta say, I never remember this. I'm not sure, honestly, if I could, with a clean sheet of paper, even remember my algebra logs well enough to do this in less than 5 minutes or something. The way that I solve for things like that is to use Excel and its goal seek function. So we will learn that soon, probably in the addendum to this chapter. We'll have a little session on that. Okay, so now let's go back to velocity and use what we just learned as another way to solve it. So another way we could solve the velocity advisors problem is to say, well, it's taking them 20 years to double our money. How long would it take a T-bond to double our money? Okay, we've got the T-bond interest rate at 5% here, so and the ratio for doubling is going to be 2. So we have log of 2 divided by log of 1.05, or about 14 years. Okay, so the treasury, we could find, what this is telling us is we could find a treasury bond that would double our money in roughly 14 years compared to 20 for velocity. Okay, velocity is taking 40% longer to double our money, so we definitely would want to stay away from that. Okay, so the good news is if you have come this far and you want to specialize in 2 cash flow financial projects, you're done. You can stop with this chapter, you can stop learning about finance, you can put out a shingle and say, I'm a finance specialist that specializes in 2 cash flow projects. But sadly, most projects have many future cash flows, and we're going to have to deal with those. So let's get started on doing that right now. Okay, so these can be solved very easily by treating them as sets, simply sets, superposed sets of 2 cash flow problems. So let's look at an example to see how this works. Okay, so let's find out how much an investor would have to pay now to purchase a bond whose contract says we'd get back in 1 year $6,000, and in 2 years we'd get $8,000 back, and the interest rate for this bond contract is 10.4%. So this is definitely not something we can do with what we've learned so far. So let's bring out the big graphic guns and see if we can figure this out. So we'll start with a cash flow diagram for this project. This is a cash flow diagram for the investor. If we participate, we're going to put money in now, so that's negative. Then in a year, we'd get $6,000 back, and in 2 years, we would get $8,000 back, and the interest rate is 10.4%. Okay, well, there's a nice way that we can think about this to use only what we already know to solve this problem. Why don't we break this CF0 into 2 pieces? Okay, I'm going to say this piece here and this piece here. Okay. Okay. And let me, oops, we go back to our little typewriter tool. And where did we go here? Oh, sorry about that. My page is lost here. Okay, here we go. Let's call this piece A, and let's call this piece B. And so then CF0 is equal to A plus B. Okay, and once we make that simple move, we can say we have a problem here where we have an amount of money A growing for 1 year at 10.4% into $6,000. And we have another amount of money we put in at the same time that's going to grow for 2 years to $8,000. And each one of those is growing at 10.4%. Okay, this is also growing at 10.4%. Okay, so now I think we can solve this. We just apply the present value version of our fundamental time value formula to solve for A. Okay, we know 6 is our FV, 10.4% is our interest rate, our time is 1 year, so we can solve for A. And then for B, we do the same thing. We know our future value is 8K, our interest rate is 10.4%, and our time for this one is 2 years. So we solve for A, solve for B, and then just add them up, and we'll know the total amount we have to put in for this project. Okay, so let's go ahead and do that. So A is equal to, well, let's say A comes from, so I can show you where everything starts here. PV is equal to FV divided by 1 plus R to the 1, okay, and B is going to come from PV equals FV divided by 1 plus R to the 2, and that's equal to B, and this is equal to A. Okay, so we can plug in now and say that A is equal to, I'll clean this up a little bit in a second. Let me just finish here. PV is equal to 6 divided by 1 plus 10.4% raised to the 1. So let me say here FV1, and just to make sure we're clear that we're talking about the 6,000 and the 8,000, so I'll say FV2 here. Okay, so working that out, substituting in, A is going to be equal to 6,000 divided by 1.104 raised to the 1, and similarly B is going to be equal to our 8,000 divided by 1.104, that's 10.4%, by the way, the raised to the 2, okay, and then again, CF0 is equal to A plus B. So that's pretty good. it's very important that you understand everything we've done on this page, because this we're going to use through the rest of this text, and you're going to use it through the rest of your life in finance, anything you do with finance. So please make sure you understand exactly what's going on this page, okay? And so if we work it through, you can see down here that I've got everything solved for you here. And so much for that brilliant idea. I'm having a little bit of trouble drawing boxes here, but we won't worry about that. But the final steps after plugging in show us that A is equal to 5.44 thousand, and B is equal to 6.56 thousand, and CF0 is equal to the sum of those, which adds up to 12,000. Okay. And another way we can think about this is that the 12,000 that the investor pays for the bond is comprised of two parts. $5.4 thousand tranche for the $6,000 repayment, and another $6.6 thousand tranche for the $8,000 repayment. So that's also a very good way to think about it. Okay. Another way to think about this in terms of cash flows is cash flow zero is the present value of all of the investors' future cash flows for this project, okay? And so we're going to start calling that PV tote, okay? So we'll say CF0 or PV tote, okay? It's the sum of the present values of all the cash flows for this project. So first, take the present value of each cash flow, then add them up, okay, to get CF0. All right, so let's see once again if we can get a general case for this. I think that we can do it. Okay, so the total PV, what we're going to start calling PV tote of a set of future cash flows, is, as I said on the last page, the sum of the individually discounted cash flows. Discount them first, then add them up. Okay, so let's be a little mathematical. For a set of future cash flows, PV tote is going to be the total present value for this set, PV of first one plus PV of second one, et cetera, et cetera, et cetera. And now we can apply summation notation to this idea and get what is a pretty elegant formula, okay? So the total present value of a set of future cash flows is equal to every stinking cash flow in the set, every future stinking cash flow in the set, first individually present valued, brought back to its equivalent at t equals 0, and then added up. Okay, so for each cash flow, discount it, and when we've got that done, add them all up. And when we look at the equation this way with summation notation, we call it the fundamental discounted cash flow equation. And this equation appears throughout finance. So this is a very important equation. Okay. And same as with two cash flow problems, we can use CF0 instead of PV tote and use our common sense for algebraic signs. Okay, so if we use CF0 instead of PV tote, then the fundamental discounting cash flow equation looks just like this. Okay. Also, a few things to note. Always good to think about what can we say about this formula before we just start willy-nilly making numbers. Well, if we're given the amounts of all the future cash flows and the discount rate, clearly we can compute PV tote or CF0. That just pops right out of looking at this guy. Okay. If, on the other hand, we know PV tote, the interest rate, and we know the cash flows are uniform, then we can compute that uniform cash flow. Why is that? Well, let's look up at this equation. If they're all uniform here, CFI is equal to CF, which is equal to a constant. And as we all know, if we have a constant there, we can bring it outside of the summation sign. So that's going to make it easy to solve for. Okay. Similarly, if we know PV tote and we know all of the cash flows, we'll be able to solve for R, but it's going to be difficult. We're going to need typically Excel and we'll see. Okay. All right. So how else should we be thinking about this equation? From a lender's perspective, PV tote or CF0 is the amount we have to invest now, the principal we commit now to receive the future stream of cash flow. So that would be a contractual agreement where I say, you give me PV tote or CF0 now, and then I'm going to give you $6,000 back in a year, for example, and $8,000 back in 2 years. Also, we can say if PV tote is constant, as the interest rate goes up, our future cash flows go up. So if we're a lender, should we try to maximize our, well, this is one of those wishy-washy, it depends kind of answers. Okay, we need to watch out for competition and the riskiness of our borrowers. If we set, as a lender, if we set our interest rates too high, everyone will go to the competition, okay? And also, the higher we set our interest rates, the riskier the borrowers we're going to get, and we'll talk about that more as time goes on. Okay, from a borrower's perspective, CF0 is the amount we can get now, get a big pile of money right now for contractually agreeing to pay the future stream of cash flows, okay? And for a borrower with the future cash flows constant, as the interest rate goes up, the amount we can get goes down. So we want to reduce, as borrowers, our interest rate. How can we, in the real world, reduce our interest rate? The best possible thing you can do as a consumer is raise your credit score. All consumer loans are keyed more than anything else to your credit score. Of course, if you're an undergraduate in college right now, you don't have a credit score. Good thing to do is get a credit card as soon as you can in your name, not guaranteed by your parents, and spend a little bit on that credit card every month or two and pay it back promptly, okay? And that will help give you, within 2 or 3 years, a pretty high credit score. All right, let's do another example. So Velocity Advisors offers to pay you $6,000 at the end of next year. So that would be cash flow 1 at end of year 1. EOY1 stands for end of year 1. And they're also going to pay you $12,000 at end of year 2. In return, what do they want for that? They want your payment now at t equals 0 of CF0. And the interest rate on this deal is 10%. So let's see if we can find what is CF0, and also let's answer the question, if you have just 15,000 to invest now, can you participate in this deal, yes or no? Okay, so let's check this out. Okay, um, so the solution here, let me just see if I have a cash flow diagram for this one. I don't have a cash flow diagram for this one, but I think maybe I should just go ahead and draw one. So let me go ahead and do that. So here's our x-axis, and we're going to put in CF0 now. Okay, and in return, we would be getting 6K in a year, and we would be getting 12K in 2 years. Okay, so I think that's pretty good. All right, so here's our CF0 equals A plus B as usual, and up here we're going to get 6K back, and up here we're going to get 12K back. Okay, and this is diagram for the lender. We're going to be lending them our money. Okay, and then as usual, we have CF0 is equal to A plus B, so that's going to be this piece here plus this piece here, A and B. Okay, whoops. And so here is A, oh, not the one up there. There's A, and there is B. Okay. All right, so again, this is pretty straightforward. We have piece A is going to grow at the interest rate for the project, which is 10% for 1 year. And piece B is going to grow at the interest rate for the project for 2 years and wind up being 12,000. All right. So let's just put in our interest rate here to make sure everything is clear. It's growing at 10%. This is also growing at 10%. All right, so that's the basic idea of what we're doing, and we'll just do this in the framework of the fundamental discounted cash flow equation here. Okay, so I've got all the work for us done here. CF0 is going to be equal to that first payment divided by 1 plus r plus the second payment divided by 1 plus r squared. So I substitute in, and first payment is 6,000. R is 10%, so I have 6,000 divided by 1.1, and second payment is 12,000 divided by 1.1 squared, so that's 4,500 roughly, plus 9.9 thousand, or 15,370 dollars. Okay, and remember CF0 is that portion corresponding to the first payment and the portion corresponding to the second payment. So in the terms of the cash flow diagram, it's A and B as noted right there. Okay, so that's all good. And I still need to answer the question though, could we participate? And as you can see here, I've got the answer. Okay, we only have 15,000, and we would need $15,370, so we cannot participate in this one. Okay. All right, and on that note, let's take a short break, and we'll be back quickly.